Hello everyone, I'm Ting Wang from National Tsinghua University. Today I'm going to talk about an extinction-free agent census by 23 space-based infrared band ACD. Basically this work is about observation. I will briefly introduce about AGN. AGN is active galactic nucleus. This is a compact region at the center of the galaxy, and this is a very luminous source. And also, it has been widely believed that there is an AGN in every supermassive black hole, and the mass of the supermassive black hole is related to the bulge mass of the galaxy. Therefore, if we want to have a better understanding of the galaxy evolution, it is very important for us to find AGNs. Actually, there are several ways to find AGNs, such as optical, UV, and soft X-ray observations. But there are some disadvantages. Like this is the dumpling, as we see there are many colors, and but it's difficult for us to find some dumplings, right? So if we use some optical observations, we will face the similar difficulties. Therefore, here comes the questions: how to solve this problem? The mid-infrared survey can help us to find the obscured AGNs because AGNs perform the strong thermal emission in the mid-infrared wavelengths. If we use mid-infrared survey, we can find these obscured AGNs. But star-forming galaxies also perform high, strong path features in the mid-infrared wavelengths. If you want to use the mid-infrared survey data, then it's very important for us to separate AGNs from star-forming galaxies, so that we can see how the AGN affects the whole galaxy, apart from the star-forming activity in it. And there are many some famous infrared surveys such as Spitzer and WISE, but because in WISE and Spitzer survey there are gaps between each filters, if the feature of the AGN at certain redshift located at the gap, then we might not be able to find these AGNs. But AKARI can help us to solve this problem. The AKARI is an infrared space satellite with continuous 9-band filters in the mid-infrared wavelengths. And in the NEP wide field, the coverage is 5.4 square degree. As we see in the right figure, the gray circle is the AKARI coverage. So compared with WISE and Spitzer, we can construct a more complete infrared photometry of each galaxy with AKARI. And Songjin Kim is one of our collaborators. He made this band merge catalog. In this catalog, we use 36 filters to construct our sample, including Subaru HSC, Majdanek, Flamingos, Spitzer, WISE, AKARI, CFHT Megacam, WeirCam, and Herschel Park's Spire photometry. So this is our data selection. Actually, there are around 92,000 samples in the catalog. And because of our method, we need to make some constraint. These sources must have a far infrared detection. So the number of samples is hugely decreased. Also, I want to specify for our SPECZ sample, we already have the AGN classification catalog. So in this work, we construct two samples. One is the SPECZ sample, one is the OZ sample. For the OZ sample, it includes the SPECZ sources and photometric redshift sources. We check the feasibility of our AGN selection first with the SPECZ sample, and then apply our method to the OZ sample. The ACD fitting code we use is SIGAL. SIGAL is a spectral energy distribution code derived by physically motivated modeling based on the energy balance between the UV and far infrared wavelengths. So that it can, because it's an energy balance mechanism, it can provide us the physical properties of the galaxy, such as star formation rate, AGN luminosity, or dust luminosity. How can we find AGNs with SIGAL? In SIGAL, there's an AGN model called BRITS 2006, and there's a free parameter called AGN fraction. It means fractional contribution of AGN emission to the infrared bolometric luminosity. In order to avoid misunderstanding from other works, we use AGN contribution instead. In SIGAL, we set AGN contribution from 0 to 0.7. And I also attach two figures. For the left figures is the typical shape of the star-forming galaxy. As we see in this part, it's a stellar bump and the dust bump. But if it's AGN, it will perform a power law light because the thermal emission from the AGN can fill the gap. Just briefly show you the parameter I use in this work. Okay, so after we run the SED, we compare our result with the AKARI AGN criteria box from Li et al. 2007 and the WISE AGN criteria box from Jarrett et al. 2011. So basically, we can see many of our sources. We here define if the AGN contribution is larger than 0.2, then it's of high AGN activity. And we can see many of the sources are located in this box, but still some are missed. But if we double check with the spectra AGN and the Chandra, because these AGN classification of our SPECT sample is done by spectroscopic survey and Chandra X-ray observations. And there are still some outliers. And we believe that this is the AGNs we missed from the color diagram. Sorry, this might be not so clear, but most of the sources of high AGN fraction lies in this box, but still there are some outliers. So this is what the goal we want to reach. We want to find a more complete way to classify AGN. And also in our SPECT sample, we identified two quasars at a redshift higher than 2.5. And both of the sources are of very, very high solar luminosity. I attach one example. As we see, this source performs a power law like spectrum, and we also carefully check with the image. It's a point source, so this is a quasar at redshift around 3.363. Also, this figure shows the total infrared luminosity as a function of redshift. As we see, it follows a curvature trend. When the infrared luminosity is higher, the redshift is also higher. Also, different colors refers to different AGN contribution. Galaxies with higher AGN contribution tend to have higher luminosity and higher redshift. But is AGN contribution redshift dependent or luminosity dependent? We separately discuss about it. As we see, if we plot the AGN contribution as a function of total infrared luminosity, this is basically flat. It means there's no clear relationship between the total infrared luminosity and AGN contribution. But the AGN contribution of the sources at higher redshift beam is higher than those at low redshift beam. If we plot the AGN contribution as a function of redshift, we can see there is a trend. So it might imply that AGN contribution is redshift dependent, and we may find more AGNs at higher redshift. Also, we do the same thing for our OZ sample. So basically, the results are similar. It also shows no clear relationship between the total infrared luminosity and AGN contribution. And also there is also there is a relationship between redshift and AGN contribution. So this is my summary. There are high possibility that there are high AGN activity if the AGN contribution of individual galaxy is higher, and we expect to recover more the subscribed AGNs with this SAD fitting approach. And AGN contribution of an individual galaxy is higher at higher redshift. Finding previously missed AGN is important to figure out AGN star-forming galaxy coevolution. But we still have limited sample because of a lack of long wavelength photometry. We expect SCUBA 2 data can let us have more accurate SAD fitting results. And also, with the launch of JWST, we will have more high-Z sources. And if we apply this approach, we can confirm if the trend of the redshift AGN contribution relation will be more clearer. This is my talk. Thank you very much.
Have you tried to classify type 1 and type 2 AGNs? And if so, do you see different AGN contribution dependence?
That is what we are doing now. Yeah. So it will be updated.
Okay, we can have one more.
About your summary, the second point, I think it might be right, but it's very difficult for me to understand here because what you show, you're using the spectral Z, AGN, right? And you show there are higher fraction and high Z. But for those AGN, usually they are more luminous in order to have the spectral Z. So how do you separate those in Melquist bias?
Actually, we divided them into several luminosity beam to see the relation, but you mean this plot?
Yeah.
So actually,
No, what I say is for those AGN at high ratio, they are in principle, they are intrinsically much brighter. And that's no question that you get a high AGN friction. That's my question.
And to answer that, we separate these into luminosity fins. To see how both different luminosity beams and redshift beams. So when she compares at amount of redshift, it's in the same luminosity beams. Normal missed bias.
How about dust temperature bias?
Dust temperature. So we just separated in luminosity beams.
Because for higher redshift, it's easier to select objects with higher dust temperature. And those are typically AGN.
Okay, we separate in luminosity beams. That's as much as we did.
Okay.